Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you would like to follow along, please don't hesitate and welcome. Today we will continue making the disassembler. If you have any questions, you can post them on Twitter or YouTube and I'll be there to answer. With that in mind, I will open the project. Alright, so if I remember, the last stream we worked on this part of the code where we were trying to specify a usage code for the extraction of the pretty much the translation of the opcodes. And I mean we didn't finish on the whole to specify it, so probably that's one of the things that we want to do. And yeah, so as you can see here, I mean it goes pretty straightforward. It doesn't have any kind of crazy stuff happening. It's just, hey, I mean we have like we define this concept of grouping. We create a big group every time that we need it to, every time that we have a, like, let's say a hint to create another group, let's say another group of meaning of the opcode itself across inside an instruction, which is the way that we define. Let's say we have two groups right now, the prefix and the main B. So each of these has some of the let's say semantics of, or the boundaries of each of the groups in bytes. So after we define the groups, we pass them to the translator, which is the main job across many things is going to do to basically translate the opcode by to a specific mnemonic. Once we got the mnemonic, we can go and continue making the fetching of the mother rhyme, if any, and the SIB, if any. So that's where we got here, so let's try to do this part just to see what happens, to see the whole structure in here. So I would like to go to the formats, and the question that we got on the last stream was that we know that the SIV is encoded inside, where is it? Here is this is for 16-bit monograms, and this is for 32-bit monograms. Now SIB okay. Look at this. This is the answer. Okay, yeah. I mean, as I told you, you just need a new day and a fresh day to start with the right foot. And as you can see here, well, pretty much SIBs are encoded in these ways of the mother M, So this tells us that the mother M by is the one in charge of telling us that a particular SIB is present after it. And yeah, we have three types, I guess. We have an SIB present plus a displacement of 32, or an SIB present plus a displacement of 8, which is, I believe, standard. Yeah. which, if you remember, on 16-bit addressing, we don't have SI bits. What we have is SI or DI. And on 60-bit addressing, the addressing forms have to be in this format, you know. It has to have, well, the mother M's and the rect field respect some encoding that we have there, but the effective address, you know, the one that on an assembler we normally specify on the workings, have these bx plus si, mbx plus di, bx plus bp and bp. They are all, you know, they are some bases. bx works as the base, and s and di works as scales, probably. Yeah, base times the scales. Oh, this is a plus, so it's not scale. An index, probably an index, and then on displacement by itself. So yeah, base plus index, base plus index, base plus index, base plus index, an index, a displacement, a base, or more complex stuff, just the same, base plus index plus a displacement, base plus index plus a displacement, the same combinations with a displacement, base plus index, or just the index, or just the base, or, you know, the registers themselves, which in this case is telling us that we are looking at the value. Okay, 1 1 EAX AX MMX default segment register, and for 1, where is the 1? So we have a BP index here on the combination. If we have, for example, this is BP index, we have to select with the segment register with the SS. If it's not the BP index, it's gonna use the DS register, segment register. Is that encoded, or it does? I mean, probably just telling us that that happens. The nomenclature now is 16-bit displacement. So what that means is that if we look to the SIB, I mean, probably what we need to do is to decode. I mean, if we found that some SIB is encoded, to find the effective address that we are looking at, we have to first go to the SIB table, you know, which is this one, and we have EAX, CCX, EDX, EVX. I mean, we do the calculation for the scale index, but well, I mean, we have the same kind of thing, you know. We have a base, we have an index, and we have a scale, which is good. This is 1, 2, 4, and 8, I believe. So we have that kind of stuff. Yeah, look at this. So we are scaling the index, which is encoded by the EAX register in this case, ECX, EDX, EBX. EBP is EDI. ESP cannot be encoded, that's why we have a none on the ESP case. And just as here, we have EBP on the base, you know. So the base cannot, well, the nomenclature means a displacement with no base if the mod is blah. Otherwise means this error, this 32 plus ABP. We put the following addressing modes. We have an scale index plus a displacement, or a scale index plus a displacement plus EBP, or a scale index plus a displacement plus EBP. Okay. So we have okay, so yeah, we have to look at the math. So we're moving EBP. That means that we have EBP we have the base. Let me check. We have a scale, index, and the base. So we're looking here at the base, and the base has to have, let's say 101. the scale is 0 and the index is 0, we'll have EAX encoding. So that's mean, yeah, I mean scale index is gonna be EAX for this particular case that we're looking at, plus a displacement 32 if we're looking here, and the mod is 0 0. So if we go back in here and see that 0 0, we have a scale index, displacement 32. All that's encoding the base IP, and that's the effective address. Now so that means it's not totally crazy. It's just that we add the SIB at the first, because there's a scale index which basically tells us that, and we add some displacement. That's all you got. Which in the normal cases we don't have that scale index. You just have EAX and stuff like that. So if you think about it, yeah, all the scale. Oh, okay, that makes sense. Because if you remember, you have a scale plus index, or a base plus index, or something like that. You have to have an SIB encoded. So yeah, that tells us a hint about how to write the mnemonic back. So yeah. And yeah, it's added to the index because this is the index. We have rather a scale index or a base plus index or just the index, and then we have a displacement, which is all that pretty much the modern works that way. And for the register, we have, let's say, a family of these ones, So what we do here normally is to select one of these values based upon that. But if you think about it, well, each row here has the same effective address independent of the class of registers. So even though, because everything is controlled by the mother and by, so what this tells us with the rec, it's specifying a specific register which we can use for rather dependently, it depends on the other bits before that, to remember. The meaning of these fields right here, it's demanded by the opcode main. So for example, here this tells us, hey, there's two operands, and these two operands have these mod addressing things, which is the first information that we have to look, these science things. And then for the second table, we see this is the D bit, and yeah, if we find the D bit as well, let's say we find by the opcode search, by this fast lookup table, that the instruction has this two operand thing because that's encoded. So we already know that, we know that. How it is addressed? Well, we also know that because it's also in the opcode table. It should be there, So let me write that. So operand counts, addressing forms, and operand types are encoded in the tables, and based on that, and the divid as well, let me put that. Now the divid and all these special fields, for example, for conditional stuff, it has to be also checked through the tables after a table. Well, I mean somewhere there, because the condition, it works specific for conditionals, it tells us which conditional we are looking at, and that case tells us which which form of the conditional instruction we are looking for. Now that we know, because if you see here, where is the condition? Let's say we have a conditional. We have, for example, this jumping condition, and it has the conditions here. Probably well, it makes sense because they are the first 4 bytes of the opcode by, so it has to be encoded here as well. I mean, it's well, now that I think about it, it was just specifically for that. It's just because in the table, I mean, I can say it's redundant, but it's not redundant. It's just like, hey, I mean, the same information that we're looking here, I mean, it's just another way to look at it, let's put it that way. So the same information here that the opcode tells us, this opcode table pretty much basically tells us the encoding, we don't need to dig. I mean, if we want to know just encoding and the prefixes and the operands and stuff like that, we can just look to the table. But if you want the specific meaning of expressive of fields inside the main opcode, we can look at this, because these things are respected in most cases, And here we have let's say here, we have S and S, PP and MP and PO. I mean, just in the same order as we see here, S and S, PP, look at this, 1 0 0 1 1 1 1 1 1. This field is 8, so this has to be something 8, and there you go, this is the 8. So it's like, and we have the others in the other, but right here we have O and O, B, the same order. So this is respected, so that's good. And the direction bit in this case is special because if we find it, we're very well, we know when to fetch for a direction bit because the instruction itself is gonna tell us about that information. So yeah, so I think that's good. um, Now remember that the direction now, for example, well, this also is the encoding of it, and depending on the value of it, because this doesn't tell us any value, you know. Some of the instructions have specific monorems, you know, that have to be respected. For example, register 1, register 2, we have, well, yeah, that makes sense. We have, whenever it's a variable thing, we have a math here. We don't have an SIB in here, and that's probably it's because it's implicit. I mean, it's implicit in the sense that just in cases where we are looking at 32-bit addressing, and with the cases of having this encoded, so we know 00 with 100 on RM, and any of the cases for the rec register is going to encode the SIB. So I mean this, yeah, I mean this, that information is not in here. So just so, hey, this is a monoram thing, you have to look for the meaning of the monoram itself on the table. But it's just telling you, hey, this is, it's like another way, it's the same thing, you know, another way to look at the information, you know. It's like, well, you want to see the bits, well, here are the bits. If you want to see the meaning of the bits, well, you have to see the whole the whole thing of the things that we have seen. And you know, I mean, that makes sense because this table is the last table of the information that represents opcode information and instruction formatting. So I mean, it's not weird that it's at the last thing. It's nice that we have the bit fields, which is good. But I mean, the most important things to see here are probably, I mean, I don't know. For example, we have here intermediates, and we have this encoding for 101, which, if you remember, this is 101. So 101 is this, no, rec is 101, is this. So we have 101, so we have this bit field for a specific mother RAM, which in this case has to be, let me see, it's 101 rec. So it's 101 11, and RM we don't know. But it's a register just the same way. So in this case we know, because of the specific instruction that we're looking at, that the register, I mean, we're moving from immediate, oh well, yeah, we're moving from, yes, this is the register, we're moving from, oh, what, this is crazy, no, I didn't mean that, where is it? Oh, it's because I see, I was seeing another one. Okay, that's crazy. No, I meant this one. Yeah, for example, this one, 010, okay, is this one, and we're looking at this one here. So it's DL, DX, blah blah blah, you know, and we have the register, and this is moving from immediate to register. That makes sense. And that's it, you know. So the table, yeah, I mean, they complement each other. We cannot just say, oh, we're just gonna use this table and we're not gonna use the other table, because it would be not complete. So what we have to do is to look at both tables. Preferably we have to first look to this table, because this table is going to tell us, no, first to this table and see, hey, this is encoding, do bananas with it. Now find the real meaning of it depending on the table that we have, yeah. And probably this is the last table, that, well, one of the last tables, because this tells us about displacements and stuff that we do not have. The information is not, well, I don't know if no, I don't remember. Yeah, some of the modes here tells us about displacements, probably. I don't remember. It's no, I don't think so. But yeah. So we have that. What else is missing here? Just to see that information clearly. Yeah, I mean, we have that. In this case, that's the way that it's respected. We have, for example, from immediate to memory. So this is the memory here. We have to move from there. 1010. This is respected. That tells us that this is but we cannot confuse it, because if we say 1010, you know, we know that 010, it's the DX register. So do we use that DX register to encode something, or to show to the user the mnemonic of something, or the meaning is just on the register and the immediate, you know? Because we have a register, the rec field, it's blah, and the rec field that we're moving, the destination, is blah. So since it's an immediate and it's to register, it has to be this way, isn't it? We're not gonna have any kind of crazy offset in there because you're looking at the value. Normally what you have when you have this craziness is when you're moving up to memory, because these are the addressing forms that we get from memory. But when we're looking at registers, we cannot have that information. So it should be more like this, For example, immediate to memory. This memory can be encoded like crazy bananas, It all depends on 010. 010 in this case is going to say, okay, we have the DX, but the DX doesn't tell us pretty much anything more than that we are using DX as an encoder. The memory itself probably it's irrelevant. I don't know, because if you think about it, we are using DX and any of the memory things here. Let's say straight 2-bit addressing form. So we can just do anything of this, It can be anything of this depending on the mother M, and the mother M is gonna basically tells us which is the effective address we are looking at, So I think this is more respectful in the case in that sense, because well, not respectful, but this is the real meaning of it. So probably that thing is not totally thing. I mean, sometimes it has a real meaning, sometimes it's not. For example, when we're moving from one register to another register, it has that meaning, It's like, okay, so the instruction tells me that we're moving from one register to another register. Let's say we have this one, like register 1, register 2. Then register 1, we have register 1, and register 1 has a real meaning, which is whatever, whatever of these ones. But when it has a specific value, let's say this 101, 010, then it's not telling me anything, It's just probably like a signature. We can even assert it, because the real meaning comes from the immediate and it goes to the mother M in this case, or to the register destination, which it makes sense. In this case it's the same. We have registers. Whenever we have a variable here, it makes sense to look at the columns of the table. Whenever we have a specific value like this one, it doesn't make any sense, or it's not necessary at all to look at it. We have to assert it on pretty much all the cases, and pretty much we can have a, how you call this stuff, it can be like templates but like like some kind of, I don't want to call it templates, but it's like a base design. How do you say that? Interface? No, it's not an interface. Well, it's just like, I don't have the word in my mouth. When a prototype, probably. We have a first prototype of the thing that we want to see, and then we fill in the gaps or the empty spaces with the information that we have to look at. We can do something like that. What else? Register, mother RAM, look at it. We have immediate, register 100, the same thing here happening. Mod rec RAM, rec RAM, mod rec RAM. For example, byte swap has a special, well, no, this is encoding, yeah, and it's inside the main, but it has the register field. It has a wonder. Well, yeah, we cannot talk too much about it. For example, over here we have the bit test, we have the escape opcode, and we have the main opcode, and then we have modern and immediate. Here, well, the instruction doesn't tell us any order in this case. It's just, even though, yeah, we have a 1 set all the time, and we have 0, but they don't have that meaning in this case. So yeah, even the width, for example, the width, and the width has to also, I mean, the W bit has to be also checked through here on the encodings as well, because some of the instructions have them, some of the instructions does them. So it just depends on the instruction itself. So yeah. What else? Rec 2, Rec 1. This instruction has, yeah, I mean, this pretty much tells us the prototype of the instruction. We can see here another special signature, modern immediate 8 data. This works with immediate 8s. That's interesting, because immediate 8s if you remember, immediate, where is it? Immediates are sign extended if we have some special characteristics. Or is it sign extended? Yeah, if the sign extension is inside, which in this case we don't have any sign extension, so we don't have sign extension. But yeah, register, memory register, immediate memory. That makes sense. Immediate 8 register memory. This is a bit test and complement, bit test and reset, bit test and set. Another immediate, the other special signature. For example, the call one has well, it's in this case it's a new call. The signature for it is this thing and a full displacement. we have a register or a mother, and this is the mother. It's pretty simple. We have a call that's a far call. We have a different encoding for the direct one, and we have the selector and the offset. If it's indirect, it respects the also indirect is in memory. It's a memory case. It probably is yeah, because it cannot be registered, or probably could. I don't remember, but it's in. I mean, it has just two types: indirect or direct. Or direct. Okay. Convert byte to word. Okay. Simple encodings, no more RAMs and crazy stuff. CLI, couldn't throw a flag. Compare has special model RAMs and stuff because it's needed. Some immediates. Now, for example, if we found a case that since we right here we don't see any SIBs, you know, because the SIBs are encoded on the table. So what probably happens here is that even though we see here, like, let's say, for example, let's say compare two operands. Probably it's possible. So let's say I compare two operands has an SIB, you know, for example, from memory with register or something like that, where we have we're comparing a memory data section, you know, so memory data with the register, you know. So we have mother M and the register. Right here we don't have any immediate data information, but since we have the mod rec RM, we have to look at the lookup table and see, well, we have an SIB that's probably in there because of the way that we are addressing the memory itself. So yeah, I think that's really, really important. I mean, we don't see the SIB here because it could or it could not be, depending on the encoding of this. But yeah, I mean, we have to make sure that also gets explicitly visible out there. We have immediate with register, immediate data, alright, immediate data, immediate with memory, compare speed, compare W, compare stick, compare string. Okay, that's not too difficult. Some encoding specific. Yeah, I mean we can follow pretty much all this stuff, you know. For example, this is a register. This is special because it has followed the register thing. So I have an idea. Let's see if we can do it. We have the translate one, and the translator basically told us about something, you know. We can tell them to do a lot of stuff, information there, or we can start by saying, well, we have a cinemonic, you know. Cinemonic has some special information that we can use. The cinemonic has to look at and we can pretty much probably, it's not cinemonic, but EagleFly prototype. So the upprod pretty much has to have the same idea. Where is it? It's pretty much like saying, well, I'm gonna keep this for the other cases, but we have a B group type, B group, and let me change this a little bit. I'm gonna play around the thing. Probably the symbol is good. I need the size. What's the size? Well, I don't care, but operand count. Yeah, operand count. It's kind of useful. Mother and person. So the addressing attribute has to be resolved in that call. That's important. The operands have to be also resolved there. Well, at least the operand attributes. Probably, I mean, I'm trying to think about, probably we can return 2 of these, you know, we can have, it depends on the data information, because let's go step by step because I cannot see it clearly. So let's say we have a EagleFly up prototype here, and we got an up prototype there. We are going to use the up prototype to pretty much tell us ourselves what we are looking at. Now the up prototype is going to fetch pretty much a fast lookup table, you know, that's all we want. with special considerations, of course, about the prefix B group and stuff like that. Now, if you see here the information, it's pretty much crazy encoded. So the information has to be already decoded so that we see, hey, we have which of the data information we are looking at. For example, we found out that we have the decrement. Let's say we have this instruction, decrement by 1 with register. So we have the mnemonic, and we have other extra information about the register. So yeah, I mean, these are good. We are going to use it. And the mother m person can go this way. I believe we had I believe I had something max. I can call it. Where is it? I don't know how, if it's too complicated to think like, I mean, the translators do two things at a time. One is to decode and have some special data information that helps the parser to continue the parsing stuff, and as well it has this instruction creator, you know. The thing I don't like about that, it's like, it's not too implicit, you know. It's not intuitive, that's the word. It's not too intuitive the way it works. Right here we're saying like, hey, this is gonna go out and stuff, but in any case, I don't know, it would be better to do another call here, you know. You can even go a little bit wonky here. We can say just pretty much clear here, like. I believe I already have them. Okay, we can use this stuff. I like this way to do it. I prefer this API. It's more error prone. That makes sense. Of course, we have to. This tells us like, hey, we have this certainty. We already constructed all the things that we have done, and we just as a pass do the printing. So let me think about this. We can continue using the let's say we have member group, and I want to pass member group as well, member group is already pointer. Okay, so yeah, I want to pass the pointer because I want to modify here as well, so the range gets a little bit better encoded. And so probably now I think about it, we don't need the main big group. Yeah, because the main big group so we can do it like this. Yeah, like it is more. And depending on the upprod, stuff like that, we can start pushing forwards here. Now we can here say if, depending on the decoding of the modern by, if, what is it, probably, well, I don't have it here, but I'm gonna say here. in this case, I'm gonna call this now if you see here, what I'm trying to do is to have a intermediate representation of the data, which I don't know if super important. I mean, it was like kind of, I mean, the first, that's why I'm trying to do the, for example, the prototype and stuff like that. But I'm trying to think of any good reason why not to do it. Because, well, if we don't do it, one, it would be pretty much simpler, since, I mean, well, the semantics of the function calls would be to pretty much print the data out. But since we're forwarding the printing to be afterwards, I think it's it's not too bad. It's not too bad. The only thing that I'm trying to see here is like, well, we have some data information. There's all these symbols, for example, especially these two, have to come from lookup tables as well. in the upprod, I don't know if the upprod, yeah, we have a symbol here. Now, this is not super necessary because the data information has to go into it. What I want is the relevant information to the SIB itself. But the SIB, I believe it can go into the same thing, you know, because the SIB, even though right here I'm using as a pause pass, I believe we can do this inside the mother RAM as well, because we need to decode it, all the information in one pass, if any. Now the displacement stuff, we are gonna know it based upon that, so all that information has to come as well from there, which is good. Now yeah, so I can call this pretty much the code. So I don't know what I think I like this, you know. It's a first pass, but I think it has the things that we want. I don't need this. We don't have this anymore. I want to think here. Well, yeah, I prefer it. I mean, I don't see any reason why not to keep it statically. Now, depends on the information, but I want to keep an allocation of it. Now, the black copy could be huge. Now, if I have allocation in there, it's not gonna be a problem. Just in the case that but we don't need to keep it. I mean, that's the whole point of it. We can reuse it the whole time. Now, because everything's gonna be used by the IP, we're gonna use the IP as a controller, even though we use, I believe, C5 control pointer by. That's the thing. For example, one thing that's missing here. Anything on each pass of instructions, we will reveal the opprod. And yeah, I mean, we don't need to keep the other opprod by any means. It's done serially. So yeah, I mean, even though it's a black copy, I can pass it. I mean, I don't like it because it's a huge thing and probably it's gonna be bananas. So we can reuse it, I guess. I mean, even though we can do this something like this, you know, it's totally the thing that I could say. You know, some constructor that we can use. And in that case, yeah, we're just gonna reuse it. So yeah. What's this? The code surpass identify. Okay. Okay, my dear. I can play with you so as long as you want.
gonna call this add opret. Okay, so we did that. Okay, it's good, it's good, I like it. So now it's time to implement all the stuff, all the function calls and stuff like that, which is not pretty hard, since we already defined the usage code here. Let's just play around. So I think I would like to start by the simplest thing here. Probably the printing stuff. It's not gonna be too hard to do. You can't even do it. Well, well. Well, if you see here, I'm gonna just simplify this stuff. Well, yeah, I like this one here. I don't know why. Alright, so I think, let me compile this. Now you see here, he didn't tell me anything about this pointer stuff since it's a core and you're passing an int. I believe yeah. I mean, I still have it to do to make our own printfs.
But hey, one step at a time. Alright, so yeah, I like it. We're getting somewhere. So I think I'm gonna stop here, but we will continue on this on the next stream. And you know, we pretty much have a good usage definition here. Now we can start working with it, so I like that. And yeah, we will continue with this on the next stream. So thank you very much for coming up, and yeah, if you have any questions you can post them on Twitter or YouTube and I'll be there to answer. With that said, I say thank you very much and I'll see you all on the next stream.